Hey, this is the second segment of the running water chapter, and I stopped right before the flooding. It was the capacity and the competence. Remember, the competence is the maximum size sediment the river can carry, and the capacity is the total load of sediment in the water. And we are right now on the flooding, and we're talking about flooding when the water actually flows over. Here is the channel, and the water level rise over the channel. It comes out, and it will cause flooding. um, the flooding is very natural process on any river, every river, and we describe it by how often it happens. And as you probably know, we have 10-year floods, 50-year floods, 100-year floods, 500-year floods. These are important to remember, that these numbers are just statistics. All you do is you can add up the number of floodings and divide it by the duration of that time, and that gives you the recurrence interval, which will give you 100-year flood, and it shows you the area, how big is the 100-year floods, the 10-year floods, the 50-year floods, and so on. So basically, it doesn't mean that if you had a big flood, then now you won't have another one for 100 years. It could happen like 3 times in the same year. It's just statistics, as I told you. Um, the flooding can cause great damage in heavily populated areas. I mean, you all have had experience with some kind of flooding, so we all know this. And because of the very, very fast moving water, it has very huge energy, so therefore it can make great erosion. As you can see on these pictures, like this house was kind of moved to a bridge and all this other stuff. uh, I guess you all could tell me some flood stories, because people have experienced floods throughout their lifetime. When the water slows down, uh, and all this sediment is in the water, it's going to be deposited usually on the floodplains. And so very many times, all the organics material being deposited are making very good soil, and the soil quality along the rivers are usually very, very good. So those areas are where we have the best quality soils usually. Today we have to talk about a little bit different floodings. We can talk about the so-called urban flooding. Because of all the land around big cities are all covered with asphalt or concrete, so therefore the infiltration capacity of the ground is very small, because when it rains, the water will run off into the sewage system. So therefore, basically, the ground doesn't have any infiltration capacity. So that means that when you have uh, big rains, basically the flooding happens very quickly, and it's very, very high level. Where normal cases it was different. The flooding peaked later after the rain, because of the ground actually sucked up a lot of the water, and so therefore it took longer for it to start flooding. Today the flooding is much faster and much higher, at peaks at much higher levels. The other thing you have to know about is the flash floods. The flash floods is because of all the ground cover. So as soon as it rains, basically the flooding happens right after, and the volume is going to be really large, and the duration is relatively short, and it triggered by heavy rains usually, as we all know. So this here shows you, this is the original river. So it shows you the floodplain and when it's flooding, really. What can we do about flood control? We can actually design dams to trap flood. Uh, so when it's flooding, the water is trapped in this reservoir, and then it slowly can be released back into the environment. You can have artificial levees made. That's when you actually increase the elevation of the river bank, so it can handle more water in the channel. And you can also do wise land planning, which is the smartest idea in my opinion. Basically, just leave the 100-year floodplains alone. You don't build anything there. Most of the time, of course, you know that civilization uh, founded on rivers like the Nile, the Euphrates, like a lot of these famous rivers are all surrounded with big cities, just like the Mississippi River in the US. So to say that just don't build anything on the 100-year floodplains is easy to say, but it's much harder to do, of course. So we finished with the flood, so now let's talk about the types of the streams. Basically, when you look at the longitudinal profile of the stream, the alluvial fan is going to be up here, the braided stream is right here, meandering stream is when it's flat, and the delta is the mouth of the stream when it enters to the ocean. So these are the 4 types of stream we're going to talk about, and you will have to know them because I will ask, please list the types of streams and characterize them. So here is the longitudinal profile. Remember, at the headwater, you're going to have the alluvial fan and the braided stream, meandering stream, and the delta. So let's start with the alluvial fan. What we have at the alluvial fan, usually it happens actually in very dry desert conditions. So in those areas when it rains heavily. So what we got here, usually steep slopes, very much rain at one time. So the water comes down really, really fast, can carry a lot of sediment, lots of energy. And when it gets to the foot of the mountain, what happens? Look, the gradient is really steep, lots of sediment is in the water. It gets down to the flat area, and all it can do is just settles the sediment right away. So that makes the channel to split, and in between the channels you have all the sediment, like making a delta shape basically. So the alluvial fan, usually in these fan you have very polymiced, which means every kind of grain size and grain shape and type of rocks in there, very immature, and this sediment is very high energy, huge big grains, usually big conglomerate or breccia size grains. This is just another really great picture of alluvial fan right here. The next type of stream is the braided stream. When you have a braided stream, it's characterized by a network of interconnected rivulets, and there is a lot of sediment bar around them. Usually it will happen close to the mountains where the gradient is still pretty high, so the river coming down relatively fast, but as it comes it gets slower and slower, so it puts down a lot of sediment, and so therefore it will have a lot of low sediment bar. There's a great picture of a braided stream right here. So braided stream, here are the rivulets, big sediment bars, and the next one is the meandering stream. When the stream is going through a completely flat area, you have to imagine that there is this wide valley, very shallow, and the stream is flowing on this absolutely flat area. Because of the centrifugal forces of the earth, most likely, it will start making these big so-called meanders. But when the stream goes into the meanders, you have to imagine yourself driving your car in a very curvy road. So what happens when you drive into a curve to the right? If you have a passenger in the passenger seat, what's going to happen with the passenger? As you go into the curve to the left really fast, the passenger feels like they are gonna fly out on the right of the car. That's the centrifugal force there. Now when you go into a left curve really hard, what's gonna happen? You're going to the left and the passenger is flying out to the left. So as you go into the curve, I hope you can feel it going into this curve right here. And so the water goes faster on this side and hits this curve hard. So you will see erosion on this side, and we call it cut bank. Cut bank. On the other side, it's much slower water movement, so you will see actually sediment being deposited, and we call that point bar. Point bar. And then you go into the other curve, and this is the cut bank, and this side is the point bar. And in this curve, this is the cut bank, and this is the point bar. So this is what we call meanders, where one side is always the cut bank side and the other side is the point bank side. Because the river is eroding this way, basically the whole channel is moving this way. Here it's moving this way. So this stream is moving back and forth on this big wide valley floor, back and forth, back and forth. And there will be times when actually the streams are... Now, before I go into that, I'm going to show you that where you have this cut bank and point bar side, the shape of the channel is going to be asymmetrical. On the cut bank side, it's always steeper, and on the point bar side, it's much more gentle sloping. And the fastest speed will be right close to the cut bank side. And same on the opposite side, it's the opposite way. So here is the fastest. When it's in the straight part, then you got the normal symmetrical with the highest speed right in the middle. So just remember that. Now, as the streams are meandering through the area, when you play this slideshow, this actually is animated, and you will see how the so-called Oxbow Lake is forming. Oxbow Lake is when the curves are going like this. They are getting closer and closer to each other until they actually will cut through. And so now the stream is going like that. And this area is going to be cut off from the river, and we call this Oxbow Lake. Oxbow Lake. Most of the time the Oxbow Lake will fill up with sediment, like everywhere here you can see it. There are some areas where you still have water in them though. But most of the time, especially if it's a dry area, those Oxbow Lakes are just going to dry up. And the only way you see it when you fly over and you see the sediment being different color. Here is the formation of a typical Oxbow Lake right there. The last type of river is the so-called delta. When you have the river coming into the ocean, and here is the ocean. So you know that the ocean water is moving back and forth, the waves. And the river is trying to come in, and the ocean is coming against it. Basically, when the river gets to the entry of the ocean, the speed goes down to almost zero because the ocean is going back and forth. And the river is trying to come in. So it actually almost stops as it's right at the mouth. So it has to put down all the sediments because there is no energy to carry it. So therefore, the sediment is being piled down right at the ocean, which forces the channel to split up into smaller, and you have a lot of sediment being settled down there. So the form is again delta, just like with the alluvial fan, and we call this delta. So here we are, a couple of pictures of deltas. That's a typical one. I thought that was a couple, but obviously there is only one. So now we are at the stream as a system. We are going to have to look at the fluvial system as a system. And when we're talking about system, we have to talk about drainage basins. So what is the definition of a drainage basin? The drainage basin is the total area drained by a stream and its tributaries. So if you look at, and before I go on, I have to tell you, a tributary is a stream which is going into a main stream. And the other thing I have to talk about is divide. The divide is the highest elevation area which actually separates different drainage basins. So in these pictures, this here is one drainage basin and this is the other. And they are actually separated by the drainage divide. So drainage basin, tributary, drainage divide, and the biggest, most well-known drainage divide is the continental divide actually. Before I get there, this slide shows the drainage basin of the Mississippi River, which is basically 1/3 of the USA. And it's bounded by the Appalachians on the east and the continental divide on the west. So that takes us to the continental divide. Mississippi drainage basin is actually 1/3 of the US, as I just said, and rivers like the Ohio River is one tributary to the Mississippi River. You also have to understand that every single tributary has their own little drainage basin. So this whole big drainage basin is divided into smaller sub-drainage basins, if you wish. So you have to understand that every single valley is a small little drainage basin, which belongs to a bigger drainage basin, just like that. So this slide shows the continental divide, and as you can see, it's mostly going through the Rockies, and you can cross the continental divide like here. This is Yellowstone. It crosses Yellowstone a lot, and then in Colorado a couple of times, New Mexico, and so on. Anytime you cross the continental divide, there will be a sign saying that now you're famous because you're crossing the continental divide as we speak. So this takes us to the longitudinal profile of the stream. Every stream shows this so-called concave up curve as a longitudinal profile, where the steepest gradient is at the headwater and the lowest gradient is at the mouth. And the result, the concave curve, this concave up curve, is the result of the controls in the balance of erosion and deposition, the balance of deposition and erosion. And if it's completely balanced, then the longitudinal profile is going to be this nice, absolutely flat, like it's just a very nicely shaped concave up curve. And that is when we call the stream actually graded stream. It's a smooth, that's the word I was looking for. So when the stream is graded, that means that there is a balance between the erosion and the deposition, and the longitudinal profile is a smooth concave up curve, just like that. So that's the stream's longitudinal profile. Now the base level. You know, the base level is the lowermost level the streams can cut down. And it could be like a temporary base level, which could be a lake in a mountain, or every stream actually cuts itself down to the ultimate base level, which basically is the sea level. Now my question is why the sea level must be the ultimate base level. You're right, it has to be, because if it cut down further than the sea level, what makes the cutting down? Yeah, the gravity. So if it happened to cut down deeper than the sea level, then it would have to come up to enter the sea. So it's impossible, because rivers cannot flow against gravity. So therefore, the ultimate base level is the sea level. So if you think about the stream gradation, you have to imagine that when the mountain comes up and the river starting to flow down, they have a very, very ungraded profile, because it just hasn't been balanced. The erosion and deposition is not balanced yet. So the river is full of waterfalls, lakes, waterfalls, irregularities. But when it's graded, then it's an absolutely nice, smooth, concave up curve. That's the balanced or the graded stream. So this just shows you graded and ungraded profile. Ungraded is when it's full of waterfalls and stuff like that. I just put this slide in to see what's happening with the Niagara Falls. Here we have a very, very resistant rock type, and below it it's a less resistant, so it can erode away, and you're gonna have this so-called nick point from the more resistant rocks, and underneath of this is undercutting. But basically through time you will have rock falls here, so this is going backwards. And then now they don't really want the Niagara Falls go to Canada, so therefore engineering work is stopping the erosion there. So the Niagara Falls is going to stay where it is. So the next thing we have to talk about is the drainage patterns. Basically, the drainage patterns is defined by underlying geology. And so if you fly over a land and you look at the drainage pattern, the way the rivers and the tributaries and the drainage basin and the divide looks like, is defined by the underlying geology. So flying over, you can tell the geology from the topographic features or the drainage patterns, we can say. So these are the four you got to know. You got to know the dendritic, the rectangular, the radial, and the trellis. Start with the dendritic drainage pattern. The dendritic drainage pattern is the most common. It looks like the branching Christmas tree, and that just means that it develops on regions which have homogeneous rocks underneath. So there is no any preferred direction. That just means that the weathering has about the same resistance on every rock. The next one is the trellis drainage pattern. It usually forms when we have folded topography, and we have that in the Appalachian. Like if you go up to McAfee's Knob and you look out from the McAfee's Knob, you see perfect trellis drainage pattern. So please go up and take pictures. Actually, as you go up to McAfee's Knob, you can take the whole picture project in one trip up and down. So it's about 4 hours, and you have the whole picture project behind you. So I think you should really do that. So this is the so-called trellis drainage pattern. The next one is the rectangular drainage pattern. When you have rectangular drainage pattern, that just means that the streams are usually perpendicular to each other. And this happens usually when you have limestone underneath. And those are the areas where you have typical rectangular drainage patterns. And the radial drainage pattern, which is the last one you have to know, is usually forms around central elevated points, such as a volcano, and it will actually show this round circular pattern. Like you can see that the rivers are coming off from the volcano like this. Oh, and this slide shows the exact same thing I just talked to you about it. And this also this is the dendritic, and that's radial. Now we have to talk about the stream system development, or the Davis cycle. This physical geographer, William Davis, have proposed a theory of landscape development and describe the cycle of erosion, which actually shapes the land surface. And he said that the river cycle, the erosion cycle, or cycle of erosion, sorry, have 3 stages: the youth, mature, and old age. When the streams are in youth age, that means that they are very youthful. If you look at their longitudinal profile, they are ungraded. That means that they are full with waterfalls and rapids. Very good example is the Grand Canyon of Yellowstone. This is the Grand Canyon of Yellowstone. This is a place you do not want to miss before you die. So in this case, you can see the waterfall showing that the down cutting is very intense. Usually you have no floodplains. The river is in the V shape on the bottom of it. And as I said, most of the river's energy is going into down cutting, making the river channel. That's another typical V shape, you know, the youthful stage. When the river becomes mature, then the river starts to like curve a little bit. It has a little bit of floodplain, but still most of the energy is going into widening the channel. Not that much deepening anymore, but still widening the channel. And when the river is in old age, then you got absolutely flat area. We call it peneplain, and the stream is meandering. And the energy is not going into widening or deepening. Most of the time you have big, very well developed floodplains, and there is a whole lot of floods going on. The old age actually Davis thought was the end, and it wouldn't develop into anything else, but it would be staying there for a long time. But today we know, because of plate tectonics, that sometimes there is uplifting which actually renews the cycle. So this shows a mature river valley right here. And this slide just shows you the stages, like the youthful, the mature, and the old age. And this one shows you a so-called rejuvenation. Rejuvenation happens when you have the meandering stream, and then the area gets uplifted by plate tectonics, so the stream has to cut down again. And because the stream was already logged into the meanders, it has to cut down with the meanders. Like the Colorado River is a very good example of rejuvenated stream, and this is like the Colorado River right there. And this is a summary figure of all these stages and its characteristics, so it's kind of good to know about. And that's the end of this slideshow. I hope you enjoyed it, and I will see you at the next slideshow.